All right, so we've got a couple of very straightforward simplifications there. In the y direction, okay, so I'm not going to ask you on this one. So plus TA minus WA equals MA. And again, in principle, there could be acceleration here. If there was, it would be in the y direction. Knowing that if this thing moved at all, it was going to drop, I might have chosen positive y downwards. But in this case, I know that the acceleration of A in the y direction is 0. So all of this is 0. Okay, easy enough. Okay, we're not, again, first time we've seen this, but otherwise it's familiar territory. We're going to work in the x direction, plus t cosine theta minus tb, again, no acceleration. And in any case, the knot has no mass, so we're sure this is 0. And plus t sine theta minus ta. Again, there's no acceleration, and in any case, we're defining this knot to have 0 mass. All right, so now we have 5 fairly straightforward Newton's law expressions. The question is, do we have enough information to solve this? This should always be your next question. Do we have enough equations to match the number of unknowns? I'm not going to go through this because it will take a little bit of time. But any quick thoughts about whether the answer is yes or no?
Yes.
We still have plenty of equations, but there are lots and lots of unknowns. Let's see. We don't know 3 tensions, we don't know a weight, we don't know a friction force. Okay. So somebody just told me something that is a new piece of information. I claim we don't know the friction force. Do we know anything more other than what we've written down? And this is the key connection that comes into question. We're trying to find this, right? Okay. Yep.
Me?
Yep.
We know the coefficient of friction and we know the normal.
Okay. So this is it turns out we do need a little bit more information. The connecting point that we haven't put in here has to do with the connection between friction force and normal force. So by my reckoning in here, there are 6 unknowns and 5 equations. So we need something else. So this is where something else comes in. And this is the thing that you will see quite often in Newton's law problems. It's these limiting case static to kinetic transitions. What we know, and I'm going to ask you, who just told me about this? Yes. What actually should I write down here as an equation? You said we know the static coefficient of friction and we know the normal force. How should I finish this off with an actual equation here?
It's less than or equal to?
A little louder?
It's less than or equal to coefficient of friction.
In general, that's true, but what about this special case?
Oh, it's equal to the
Yes.
tension in V. Oh, and it's also equal to.
So that is the missing link that's needed in this problem, okay? And it will come in quite often in problems where it will come in always when you transition from static to kinetic, okay? So at this point it's plug and chug. I'm not going to do this in class. I'm going to post the solution so that you can just check it. But again, it's just plug and chug, and it's particularly simple in this case. And again, not to be annoying and leave you totally in the dark, it turns out that the answer is that the maximum weight that block A can have is 103 newtons, okay? All right, so questions on the setup and solution of that problem. Feel good? Okay. So, I know a couple of you, obviously there's a recitation in Office House today and tomorrow. A couple of you have indicated you're having some difficulty with the last problem on the homework. It is indeed a little bit tricky, it's a little bit unusual. Just try and apply our standard procedure so far, and obviously we'll have opportunities in office hour recitation to discuss that a little bit further. I guess, again, in the spirit of being a little bit more problem-solving focused in class, are there any sort of general questions? This is a little bit hard to answer. Any general questions that you are confronting with Newton's law problems that you think would be helpful to discuss quickly in class? Yeah.
On that, if you have a string of mountains and going over everything, can you assume that the tension in, like the tension in this part of the string is the same as the
Sure. Good. So the question was, if I've got a string going over a pulley, maybe it starts off horizontal, turns through 90 degrees, and then is hanging vertically. So if it's a sort of continuous string that doesn't connect with another one, that's one prerequisite for the answer being yes. The other prerequisite for the answer being yes is that the string should be massless. Okay? We may talk about the complications introduced when strings themselves have mass, and I'll tell you why that is often going to introduce a complication. As soon as a string has mass, if anything in the thing that it's connected to is accelerating, then presumably the string itself is accelerating. And if the string itself is accelerating and it has mass, then there must be a net force acting on it. So that sounds like a simple statement, but I can guarantee as you think it through, it's a little more subtle than you might think. The string has mass, it's connected to objects that are themselves accelerating. When the string is accelerating, the string has mass, there must be a net force. So that tells you that the tension on the two ends of that string cannot be the same. Okay? But for us so far, we're dealing with massless strings, and we're dealing, with the exception of this problem, with strings that are only have two ends, so to speak. There's no knots in there, there's no connections. In those cases, yes, the tension is transmitted uniformly from one end to the other. Good, that was a good question. All right, so again, quite a lot of practice this week on Newton's law problems. I want to expand our menu of forces to work with, and we've talked a little bit about this, at least some of us outside of class, the idea of a drag force. Yes, sir?
Before you move on to explain the intuition behind that equation a bit more about the frictional force and the normal force, find the strings the forces are perpendicular.
A little louder on that.
Do you explain how to think about equation? Because it's kind of strange to me that the forces are perpendicular yet still related to each other.
Yeah, I agree.
It's also weird
So
that
you might remember when we first introduced friction force, which I think was last week, I was very careful not to make this a vector relationship. So they are not in the same direction, obviously, they're perpendicular to each other. So I don't know if it's strange or not. If you recall, we talked about the microscopic picture of surfaces that to a large extent is explaining what friction is. And it's this idea that in one of the links I sent you, they use the word fractal, which isn't quite fair, but it kind of gives you a nice visual image to think about. The surfaces are rough at microscopic level. They have peaks and valleys, they have things sticking out, they're jagged, they're rough. So it's possibly reasonable to expect that the more you push them together, remember we're on our mattress spring model of materials at the atomic scale, you're tending to squish more of those rough fractal surfaces together. So there's a lot more places where there are going to be interactions between atoms and molecules on the neighboring surfaces of the interface. So is it obvious that it's proportional to the normal force? No, I wouldn't say so, but it's also not implausible. So it's a pretty good approximation, it turns out. The more you squish these things together, the more contact there is between those jagged surfaces. And since you're trying to push them sideways, it's not surprising that it at least is, if not proportional, it monotonically increases with the normal force. Okay, but it turns out it is actually a pretty good relationship. Yeah.
why is it also normal force and not just weight? Is that like an arbitrary choice? Is it often?
No, it very much, I mean, in this case, it is the weight. But remember, this was probably 2 weeks ago, we talked about how the normal force, last week, how the normal force doesn't always have to be equal to the weight, right? If there's some things that are pushing down in addition to gravity, or other things that are pulling up, again, in addition to gravity. Those two things are not the same. But it turns out it is the normal force because that's the sort of reaction force of the surface. That's the one that's driving it. Okay. All right, so drag force, what is it? It's a force associated with motions through fluids. And I'm going to call this a kind of retarding, so it's resisting relative velocity. So I had an interesting discussion with some of you outside lecture last week about the relationship between drag force and friction. I view them as not totally unrelated, but also obviously not the same thing. You have plenty of examples of this. Try running through water. Say you're in a swimming pool or in the ocean, and you try running through the ocean. It's not easy. It's much easier to run through air, but in fact there's still a drag force as you try and run through air. Stick your hand out of a moving vehicle window, and you can experience something which is related to a drag force. So the origin of it is not totally straightforward, and this is a conversation I had with a few of you last week. There's an element of it that is related to molecules of the fluid smashing into the cross-sectional area of the object that's trying to move through it. And then maybe this sort of, which was where the connection with friction came in, there's an element of interactions between the fluid molecules as they slide over the surface of whatever the object is. So it's not a totally straightforward at origin force. But what it turns out is we can certainly parameterize it in useful ways. And exactly how this force behaves is a little bit interesting. So the first thing is, I said it's retarding, it's going to resist relative motion. So if an object is moving a certain direction through a fluid, the drag force is going to be in the opposite direction to impede that motion. And so there are actually two sort of scenarios. Let me write this like this. Two regimes of drag force. For those of you who are going on to do anything to do with fluids, whether it's gases or liquids, this force will be very important. And engineering disciplines of various types, this is important for. Aeronautics, aerospace, of course. The way this force behaves depends to a large extent on what the flow of the fluid looks like, behaves like. So I'm introducing two words here, one of which is pretty well used in common language, namely turbulent, and the other somewhat less so, laminar, and they're fairly different types of fluid flow behavior. So turbulent, as you know, suggests something that's kind of changing quite often. It's maybe even chaotic. So that's a pretty good description of the context we're going to use it in. Laminar, laminate, laminar. What does that suggest to you? What type of flow? Yes, sir?
Constant?
Constant, yeah, typically. Any other connotation of the word laminar?
Uniform across the surface.
Uniform, yeah. Any other words? Similar response, yeah.
Parallel.
Parallel, okay. Yeah, it's a much more sort of smooth flow pattern. In general, it doesn't change at all. And so I think it's the time-dependent characteristic that is the distinguishing feature here. So laminar tends to be steady state. It's the same flow pattern always. Turbulent, by contrast, is changing. So the reason I kept somebody's drink mug here, which this is the easiest way I could think of demonstrating it. So some of you have seen analogous things with maybe smoke flows as well. But if you open a faucet, obviously this isn't a faucet, but I'm going to have fluid flow vertically here. It's not the easiest thing to see, but I want, once this is pouring, I want you to watch the kind of outline of the water dropping. And see if it looks different at the top and the bottom. All hard to do this at constant flow velocity. But for those of you at the front, you see anything clearly different between the initial flow and the later flow?
The initial flow is kept going
Right. So the early flow has this very sort of smooth envelope. It has a well-defined boundary, but after, I don't know, 10 centimeters or so, it's gone into this turbulent regime. So this is common for many types of fluid flow. It starts out often laminar at lowish velocity and transitions to typically turbulent flow at high velocities. We're not going to discuss fluids a whole lot in this course. It's an interesting subject. Again, for those of you who are doing various engineering disciplines, this will turn out to be very significant. Okay, so there are two different regimes, and it turns out, again, empirically, as we're seeing a fair amount of our force definitions are, this drag force, which I'm going to call it as FD, in the laminar regime, turns out to be proportional to velocity, and the drag force in the turbulent regime, somewhat interestingly, turns out to be proportional to the square of the velocity. So you will experience a larger drag force for a relative speed if you're in a turbulent flow as opposed to a laminar flow. Okay? And any of you are interested in anything aeronautical or aerospace, that will be an important piece of information. All right. So now, for the first time, I think, we have a force acting on objects as they move through fluids that is dependent on velocity. And of course, motion, acceleration, which is all what Newton's laws are about, embed velocity. So now we're introducing potentially a term that is nonlinear. So there's something now which depends on velocity, either in linear terms or quadratic terms, depending on the flow regime. So I think I'm not going to do any solutions of Newton's law with this, but just as an example, turbulent flow can be parameterized. Okay, no space there, by one particular parameterization. The details are not so important. If I ever give you problems to work out with drag forces, I'll give you a specific dependence of the drag force. But this is a fairly common parameterization. To be honest, I have no idea where the factor of half comes from. It doesn't particularly matter. There's a coefficient which does have something to do with the materials and geometries, but not in a way that's totally distinguished from two other materials / geometry dependent terms, so it's complicated. This rho term here is the fluid density, and the A term here is the cross-sectional area. Oh, and of course we need a velocity here. All right, so again, we don't have time in this course to look at this in detail. Some of you may choose to go on and do fluid dynamics courses later on. But proportional to the cross-sectional area of the object that's trying to move through the fluid. Not a surprise, okay? Think of walking through fluid, water. Think of sticking your hand out in a car. Next time you do this, just take your hand and orient it like this into the airflow and then do it like this. Of course, there's a much bigger force in the former case than the latter case. So the dependence on cross-sectional areas, this is the kind of impulse of incoming fluid molecules hitting the object. Fluid density, obviously relevant, much bigger force for dense fluids. As basically the frequency with which those molecules are hitting the object that's trying to move. And then this rather hard to define drag coefficient. I don't know how to parameterize this. It's some measure of the shininess or slipperiness. But again, quite what this embeds is not fully clear to me. I will tell you that it tends to take values that are maybe between 0.3 and 1, okay? Not so interesting for us, it's just I want you to be aware that we can parameterize drag forces in certain domains in ways like this. All right, let me have you think conceptually about dropping an object through a fluid. So, you'll see there's a couple of jars on the bench at the front of the room which have fluids in them. We're going to make use of this in just a moment, but I want you to see if you can conceptually figure out what's likely to happen here. I'm going to take an object and I'm going to drop it in some fluid. Okay, so free body diagram. Tell me what forces you can identify acting on this in terms of the forces we've discussed so far. Yeah. Normal. Okay. Not a crazy suggestion. A normal force I prefer to think of as a contact force between two things that are not moving in the plane that's perpendicular to the direction, to the surface of the contact. So I prefer to separate this and not think of a normal force, because this is not a rigid surface that is sitting on. At the back, force of gravity. Okay, should have drawn this in red to be consistent. What else? Drag force, yep, since we're specifically talking about this new drag force, and its direction is opposite to the direction of instantaneous motion. It's a little bit maybe unfair for me to draw it upwards, because maybe I don't really know yet, but let's see if we've got any other forces that we can talk about. Yeah. Weight of the fluid, that's an interesting one. So is the weight of the fluid in some sense acting on this object, and if so, how? We're going to talk about this maybe later. Yeah?
The buoyant force?
Buoyant force, okay. So we haven't really talked about this yet, but it's true, we're going to have to worry about it. I'm going to ask you to ignore it for the next few minutes. But just so that it's not totally overlooked, the buoyant force, as you probably know, is the tendency for objects that are submerged in fluids to experience an upward force. And it turns out the reason for its existence we'll explore in about 3 weeks when we do spend a little bit of time looking at fluids. But the reason for its existence, just so you know, and we're not totally overlooking this, is that in general the pressure in fluids increases as you go down in depth. Okay? And many of you who've ever dived, or dove if that's the word, will know that indeed the ambient pressure as you go down deeper underwater rapidly gets larger. So in fact the buoyant force is simply a manifestation of the different pressures at the top and the bottom, roughly speaking, top and the bottom of an object. And since in general there's a pressure gradient, it turns out there's a force imbalance, and that's the origin of the buoyant force. So, yes, in general it exists. Let's pretend it doesn't for now. Anything else aside from these two and the to be forgotten for now buoyant force? Okay, indeed, those are the only two that I can identify, setting this aside. In the absence of the fluid being here, what would happen if I just dropped this thing in, let's say, vacuum? Right, it's going to accelerate according to the acceleration due to gravity locally. All right, but now, again, just forget this for just a moment, this is dropping, so it's accelerating downwards, its velocity is increasing. And And if it happens to be in a domain where the drag force is turbulent, as its velocity increases, the drag force, which is retarding it, increases quadratically with the velocity. So ultimately, what do you expect just qualitatively to happen to an object like this? Right at the back. Right. Eventually, the drag force is going to equal the force of gravity downwards. So equal magnitude forces acting in opposite directions. What does that tell us is happening at that point? Yeah. The object's no longer accelerating. Is at a constant velocity motion. So what we should expect in a case like this is a constant, eventually, it's called terminal velocity. So eventually, so what we expect is obviously a modified motion, modified acceleration. It's not accelerating with the local acceleration due to gravity, it's somewhat less, and that amount is getting less and less and less and less until it asymptotically approaches this terminal velocity. So this is a very common phenomenon for objects flowing through fluids. The same is true if I'm in the laminar linear domain. It still increases with velocity, but it takes longer to get to that terminal velocity. All right, good. So, indeed, that's what happens. And I may, well, I probably will give you an example of working this out. Or at least I'll put it in notes for those of you who want to look at this and how you would solve the case where we explicitly solve the equation of motion, Newton's law, but now it has a velocity-dependent force in it. For those of you who are sort of getting reasonably familiar with differential equations, or even not quite differential equations, but simple solutions of nonlinear equations. Nonlinear is not what I mean. Something that has a velocity dependence, you'll see how quickly I have to solve it. All right, so let me just tell you what this looks like in this particular case. What we're going to find is that the downward force of gravity is just equaling the drag force. I'm putting a sub t here to denote the terminal velocity because they're equal and opposite in this scenario. And a simple rearrangement of this will allow us to determine that we can determine what the terminal velocity is simply by rearrangement and plug and chug. Okay? So if I've got a certain mass object, I know its weight, I know the parameters of the fluid, I know its cross-sectional area, so on and so forth. In principle, I can determine terminal velocities. I'm going to give you some values for this in just a moment. Yeah?
I was going to say that this d sub t, so that means that v is a function of time, but then where
That's certainly true. That's not what this means, however. This means v terminal. So in this case, it's not a function of time. This is in the terminal domain. Okay, so we can plug and chug here, and we get certain values. Any of you jumped out of airplanes? Yeah? What do you know about your terminal velocity falling through air? Probably you were occupied with other things rather than calculating your terminal velocity. If you reach terminal velocity in a bungee jump, I don't know, I guess it depends on how big your bungee jump is. 260 meters. Wow, that's impressive. You can. You can. I suspect the answer is no. You can calculate it. I'm going to ask you to calculate it. All right. For any of you who jumped out of airplanes or off of bridges or things, any idea what your terminal velocity is? And the question, of course, with parachutes and cross-sectional areas and things is going to be important. But yes.
About 120 miles an hour?
How much?
About 120 miles an hour.
Yeah, it is. So terminal velocity of a typical person falling through air, and cross-sectional area there is important. If you haven't done this, let me encourage you to try it someday, but if you haven't, you will have seen probably people falling, often spread eagle. That's kind of the default way, I guess, at least for beginners, of falling. Yeah, then terminal velocity is about 120 miles per hour. You will also have seen, maybe some of you have tried this, reconfiguring your orientation so that you're kind of either head down or feet down. Obviously that reduces your cross-sectional area, but terminal velocity goes up. So obviously cross-sectional area is important there. So that would be a typical terminal velocity for a human traveling through air, okay, 120 plus depending on your angle of attack.